Hello. We're going to be covering eicosanoids. As always, I have a game plan, but today I forgot to write down the game plan. Well, actually, I wrote it down, I just didn't take a picture, so now I have nothing to reference when I'm doing a voiceover, but let's just jump right into it. So, we're going to go through an overview first of eicosanoids. So, what are they, would you say? So, they're signal molecules that are involved in regulating pain, fever, inflammation, blood pressure, sleep cycle, and secretion of gastric mucosa, etc. They can be derived from arachidonic acid or other fatty acids, um, or basically just derived from omega 3 and 6 fatty acids. They are in all cells, or most cells, except for red blood cells. So every other cell can produce eicosanoids except for red blood cells. Okay, so you might be wondering, how do we make arachidonic acid? So, arachidonic acid, for starters, it is a fatty acid. So it has 20 carbons and 4 double bonds at carbons 5, 8, 11, and 14. As you can see in the picture that I've drawn here, this is just a membrane phospholipid, but how you make arachidonic acid is you need to cleave the bond there, or you can do it through other methods, but then you'll end up cleaving bonds at some point. So basically, you just cleave membrane phospholipids to get to arachidonic acid. Okay, so like I just said, you can cleave a membrane phospholipid to get arachidonic acid, but there are actually three ways to do this. So what happens first is you have a stimulus that goes to the plasma membrane, and so a membrane phospholipid. So in this case, we're going to use phosphatidylinositol. I know in my last couple of videos ago I said I talked about membrane phospholipid synthesis for phosphatidylcholine, but we're going to be talking about phosphatidylinositol for this example, but you can use a different phospholipid at some point, but for this example we're just going to use this one. So phosphatidylinositol, the first method that I have, it's really hard to see the number, but I have number 1 there. It's cleaved by phospholipase A2. So phospholipase A2 is an enzyme that releases fatty acids. So you'll end up with lysophospholipid and arachidonic acid. So that's the first way to make arachidonic acid. The second way is you're going to go through DAG. So if you remember, I talked about DAG in my other video. I believe it was, oh gosh, membrane phospholipid synthesis, to get to PC, or phosphatidylcholine. But in this example, we're going to use phospholipase C, which cleaves second messengers. So we're going to end up with DAG, and from DAG, we're going to go down instead of to the right. But from DAG, we're going to go cleave again through phospholipase A2, and then from there we get to phosphatidic acid. Remember that we can use phosphatidic acid to get back to DAG anyway, and then from DAG we can go to PC. But from this example, like I said, we're going to go from phosphatidic acid to lysophospholipid and arachidonic acid by using phospholipase A2 once again. So the last way to get to arachidonic acid is by using DAG once more, and we're going to do this by using the enzyme diacylglycerol lipase, which catalyzes like a hydrolysis, and then that releases a fatty acid plus the monoglycerol, and that's what we end up there. We end up with our products of monoacylglycerol. Oh my gosh, what a mouthful! Monoacylglycerol and arachidonic acid. So that's how we can make arachidonic acid three ways, as long as you have a phospholipid, like a membrane phospholipid. Otherwise, you're not going to make arachidonic acid, because remember in my fatty acid synthesis video that I talked about, you can't really do extra double bonds. Like, it just doesn't work like that in our bodies, like unless we introduce them into our diet. But from here we can make those polyunsaturated fatty acids just because we're cleaving them from the plasma membrane. So yeah, that's how we make arachidonic acid. So now that we have arachidonic acid, it can be converted into PGH2, also known as a prostaglandin, by pH synthase, which is also known as the COX enzymes, which consist of two isoforms, COX-1 and COX-2. This can determine which response needs to occur, whether that be pain or housekeeping functions. So the COX enzymes have bifunctional properties, or yeah, bifunctional properties. So basically, you have a cyclooxygenase activity and a peroxidase activity. I cannot tell you what a cyclooxygenase activity does because I haven't really learned it. Yes, I can Google it, but no, I'm not going to Google it right now. But pretty much the peroxidase activity will just turn that peroxide into an alcohol, so it's going to reduce it. But yeah, that's pretty much it. You get PGH2, like the first step, like the first property, the cyclooxygenase converts arachidonic acid to PGG2. Then the peroxidase activity converts it into PGH2. But as you can see there, I kind of put an X, so aspirin, ibuprofen, naproxen, also known as NSAIDs, will block COX um, activity. So yeah, let's get into the next one, which is pretty much just looking at what happens from PGH2. Okay, so the next thing I'm going to talk about is um, the pathways, or specifically one pathway from PGH2. So as I said before, or way earlier in this video, stimulus approaches the plasma membrane, touches the membrane phospholipid, you cleave it, you get arachidonic acid. From arachidonic acid, you have the COX enzymes act on it, which gives you PGH2, which is uroprocyclidin. So from PGH2, there is an enzyme called thromboxane synthase, or TXA, which will act on PGH2 to convert it into TXA2, which is your thromboxanes. So what are thromboxanes, you may ask? They are um, they induce the constriction of blood vessels and platelet aggression, and they basically start early blood clotting. So this is really important. I'm going to touch on this in a second, not in a second, in a little bit, because I want to talk about NSAIDs, and from NSAIDs, I'm going to touch back on thromboxanes because this is very important to touch on. So yeah, that's one pathway from PGH2. So before I touch on NSAIDs, I do want to touch on the activity of COX-1 and 2 and kind of what they are, because if I don't, then I can't really explain NSAIDs. So COX-1 and 2. So COX-1 is expressed in, if not most, of all mammalian tissue. It has housekeeping properties such as maintaining tissue and organ homeostasis, or like I said earlier, the regulation of gastric mucin secretion, which is very important for your stomach lining. So if you don't have it, you're going to end up with stomach pain or an ulcer because that acid can really burn your stomach lining. Um, but yeah, so COX2, which is the second isoform of the COX enzymes or PGH synthase, is only expressed in response to inflammatory stimuli, um, which elevates prostaglandin levels that cause inflammation, pain, and fever. Also, fun fact, is overexpressed in cancer cells and associated with progressive tumor growth. Um, so, which means that COX2 causes pain. So, isn't this something that we want to inhibit when we take medication? Because if we realistically, if we inhibit the pain, then we're not going to get it anymore, right? So this is where NSAIDs come in. So NSAIDs are nonsteroidal anti-inflammatory drugs. So if we inhibit COX-2, we get a temporary relief to symptomatic pain, but that doesn't mean that we're going to eliminate that root cause. So if you do have pain and it just keeps coming back, please see a doctor. Like, don't just keep relying on aspirin and all that kind of stuff. It's just not going to work unless you have a fracture. Then really, you're just taking away pain so that your bones can grow back. But NSAIDs are typically effective against low to moderate pain intensity. So if you have high pain, then NSAIDs are not really going to be as effective just because they only work with low to moderate pain. So what are common NSAIDs? Aspirin, Advil, naproxen, also known as Aleve, um, indomethacin, and flurbiprofen. I have no idea what the last two are, but if I ever figure it out, I will put it in the caption of this video or in the caption of the description, or the description, sorry. But side note, acetaminophen, also known as Tylenol, like the brand Tylenol, is not an NSAID because it cannot reduce inflammation. What NSAIDs do is they reduce pain, fever, and inflammation. So aspirin can do that, but um, Tylenol cannot, or acetaminophen cannot. So how does this work? Um, for an example, I have aspirin. It inhibits the binding of PGH2S, also known as COX, by acetylating serine residues. So in this case, it actually inhibits COX-1 here with the serine 530 on both COX-1 and 2, which reduces pain. So it inactivates COX-1 and 2 by acetylating um, the serine residue. And the problem with inhibiting COX-1 is that you won't have your housekeeping functions anymore. So, unfortunately, NSAIDs do inhibit both COX-1 and 2. So not only you reduce pain, fever, and inflammation, you reduce the housekeeping functions that your body normally does. So common side effects can be ulcers or stomach pain because of the fact that you are, let's just say, remember when I talked about how COX-1 can also regulate gastric mucosa? So if you are inhibiting COX-1, then you are inhibiting the secretion of gastric mucosa, which means that you can have stomach pain because you won't have any like film or lining protecting your stomach walls anymore. So, yeah, that's unfortunately the bad side effect. Um, but good news is that medicine these days is going towards trying to find an NSAID that only inhibits COX-2. And how does this work, you may ask? So the COX-2 active site is larger than the COX-1 active site because the fourth helix of the membrane binding domain is oriented slightly differently to provide a larger opening to the channel. So if you can make a COX-2 inhibition, like as in you can make a drug that has like it's large enough to fit into COX-2, but it's too big to fit into COX-1, then you can successfully inhibit COX-2 without inhibiting the COX-1 housekeeping functions. Now, coming back to the last thing of thromboxane, so since aspirin is an NSAID, it will inhibit the COX enzymes, so you're not going to get to PGH2, which means you cannot convert PGH2 to TXA2. So basically, you will be inhibiting um, early blood clotting, so platelet aggregation, and blood vessel constriction. So that means you're reducing your risk of heart attacks and strokes. And that's all. Thank you for studying with me.